Fluid's GPU solving right now is some of the craziest steps in speed that we've ever seen. We were benchmarking stuff a few months ago that was 20, 30, 50x speed up. A lot of people, they are intimidated by contact, intimidated by nonlinear. And I think one of the challenges there is a good FEA tool needs to have the necessary capabilities to allow you to troubleshoot. Is CFD hard to learn? I think, no. Quick answer, no, it's not. Those tools are really fast. And a lot of them, because they're newer, are actually built on GPU natively. Some people have quote unquote large computers at their disposal. Others have access to large computers per se. I think the concept of a quote unquote large computer is really being lost nowadays.
Okay, topic of general structures, fluids, and industry trends. Jim, from your perspective, what are some of the biggest trends driving innovation in FEA/CFD today?
Yeah, biggest trends. I think that we've always had the same challenges, I think, since the beginning. So the question is, what are we doing to fix those challenges, right? And one of the challenges that's always been sort of a hurdle for us is just speed, right? So I think the one of the biggest trends we have right now is just GPU computing, right? And some of the codes that we have had for decades is now getting completely rewritten from scratch, and it's necessary. It's time, right? The bottom layer, the hardware layer, is having a complete technology shift, right? Going from sort of the previous constraints of Moore's law and transistor density on CPUs to what looks like NVIDIA sort of cracking the code on that, right, and providing an unbelievable amount of computing density in their GPU structure. So, Fluid's GPU solving right now is some of the craziest steps in speed that we've ever seen, to be honest. We were benchmarking stuff a few months ago that was 20, 30, 50x speed up. We've never seen a jump like that. Even when we started getting to parallel processing, we didn't see that level. Maybe it was 2x, 3x something. So that GPU solving is incredible. We're starting to see that come into the finite element methods. With some of the code inside of ANSYS, for example, starting to get rewritten for the first time since the company was founded in the 70s. So we have some pretty interesting innovations happening on the GPU side and the speed side. The other is, I think, on the predictability, right? And this kind of brings us back into our favorite topic, Yusuf, of AI and ML. But what's the reason that we do simulation? It's to kind of predict the future. And so a lot of times our goal for creating a physics model is for it to be able to predict something that we can't easily prototype and test. And so we're seeing a lot of, I think, trends towards adopting ML and AI, not necessarily innovation. There's innovation happening, sure, but some of these tools have been around now for over 10 years, right? And so I think the adoption side is starting to build some momentum, right? And we're starting to learn how to work alongside these tools, which is different than maybe even just a year or two ago. So those are two big ones. I think the third one too is interoperability. Multiphysics is the name of the game. We live in a multiphysics world. So you don't, a lot of times I'm not going to go into FEA with an FEA only mindset, a structures only mindset. My boundary conditions for a structures model is going to imply other physics, right? Heat transfer rate is implying airflow, right? For example. And so I might simplify a dynamic problem to static or quasi-static. So, multiphysics nowadays, we're able to hook in across physics. So I can hook in my structures to my fluids. I can hook in my electromagnetics to my thermal, right? I don't have to make these overly conservative or otherwise assumptions on boundary conditions. So for me, the big three trends are speed with GPU, predictability with AI ML, and breaking down barriers with multiphysics.
Good stuff. Nice. There are a lot of FEA tools out there. So what makes ANSYS Mechanical so much better?
I think the key here is the conversation around a dedicated FEA solver software versus, I'll say, a casual tool. And a casual tool, and I mean nothing negative against that, but casual tools and casual users, like CAD Embedded, for example, those tools have a role in an initial, say, first order guess, let's say, first order simulation. And the first order simulation might be linear, it could be nonlinear, but one of the things that a dedicated FEA solver that like ANSYS Mechanical does so much better is it takes advantage of the parallel processing, takes advantage of the latest and greatest, say, convergence algorithms for contact, right? And so what I think a lot of people do is a lot of people say get comfortable in a casual tool, a CAD embedded tool, and what they're doing is limiting themselves in assuming that it's difficult to do nonlinear, or it's difficult to do vibrations, or it's difficult to do complex things, or there's no way this could possibly go faster, or I have to wait for this mesh, this single core process to mesh. Reality is a tool like ANSYS Mechanical, the FEA dedicated tools, those are constantly being innovated on to take advantage of hardware accelerations, latest, as I mentioned, GPU, and they are accelerating design engineers, if I can use that category, to simulate more nonlinear, problems and situations a lot faster. So that, to me, it's really about a tool that allows you to take advantage of hardware capabilities. The other thing too is particularly with contact, right? I know a lot of people, we've taught so many people, hundreds of engineers in linear and nonlinear methods in FEA, and a lot of people, they are intimidated by contact, okay? Intimidated by nonlinear. And I think one of the challenges there is a good FEA tool needs to have the necessary capabilities to allow you to troubleshoot, right? I mean, most of the time we're building out physics models, we're spending our time troubleshooting. And so I want to have a software tool that allows me to visualize my contact areas, to reverse engineer the model, to help me find out what a potential source of error might be. And ANSYS Mechanical has, several different ways to help you do that. So in a way, it does make you a better analyst, and being a better analyst makes you a better designer.
That makes absolute sense. Beyond traditional statistics and dynamics and statistics, what are some less well-known physics problems that FEA tools help solve?
Yeah, I mean, the finite element method is pretty powerful, right? We always align sort of FEA with structures because that's the most often used application. But FEA, that approach, believe it or not, some software use the finite element method to do fluids. That's totally kosher. It works for some cases, and electromagnetics and thermal and a lot of non sort of structural type problems. The FEA tools that we're in most often, like ANSYS Mechanical, have not only structures, statics, dynamics, right, frequency-based analysis, time-based, but also acoustics, and designing, say, the multiphysics between, say, structures and acoustics. We have the capability of coupling directly in FEA electromagnetic, electrothermal type problems for coupled physics, right? Coupled multiphysics. So a lot of products today are electronic, and so you have this engineering problem that transcends those physics. So the FEA method is ubiquitous. It's all over the place, but in particular, a dedicated tool like ANSYS Mechanical is going to allow you to solve not just structures problems, but thermal stress and coupled physics, including some fluids.
Nice. That brings me to the next question. Is CFD hard to learn?
Yeah, speaking of fluids, is CFD hard to learn? I think no. First off, quick answer, no, it's not. And that's because CFD is used to calculate, for example, single phase incompressible flow. I don't know too many mechanical engineers that couldn't learn how to solve a single phase incompressible flow analysis within a day, right? Are they going to fully understand, Navier-Stokes equations? Maybe not fully to the point they could proof it, but certainly to the level where they can understand that it's really just F equals ma, right? Fluids is really just Newtonian physics applied to a special case. So I know a lot of, say, structural engineers who are doing fluids, and if you have the right mindset to do simulation, if you're like me, you grew up playing video games, then you're going to be able to pick up the tools nowadays pretty easily. We have a 3-day CFD class, and that covers, turbulence, meshing, and heat transfer. So, by Wednesday afternoon on a class, you're ready to go. With Fluent, for example, which has traditionally been labeled as a quote unquote hard tool to learn. So, I don't think that CFD in general is hard to learn at all. Now, is your goal to end up doing multi-phase phase change with reactionary flow and chemistry? Well, then you're in for a long haul, right? Because CFD can also solve multiple layers of physics, everything from nano to micro to macro scale, right? And so, in order to get to that problem, right, that level of simulation that's going to match test data is going to take a little while. But anyone who's willing to learn is going to be able to have fun going up that learning curve for sure.
That sounds great. Question number 5. What are all the different methods for analyzing fluids? So what's the difference between FVM, SPH, DEM, etc.? And how do I know when to use which one?
Yeah, wow. So different methods for fluids. I mean, there's quite a few. The three that come to mind, right, are finite volume, right, and finite element. But I'm going to focus on finite volume, smooth particle hydrodynamics or SPH, and then a discrete particle or discrete element modeling. So, I mean, FVM, finite volume, that's the bear of it all. That does most of the heavy lifting, I think, in the CFD industry, right? A traditional method, probably the first of those three, and can solve Navier-Stokes for an insanely wide range of problems. But it's a heavy lift, right? So if I'm analyzing, for example, a free surface, right? So waves, right? So the interface between, say, a liquid and a gas, and I want to capture some of the diffusion happening at that interface, right? So I've got splashes of water into the air, I've got bubbles of air into the water. Then the finite volume method starts to slow down because you need a really, really tight grid to analyze that and to capture those details. Of course, you have to ask yourself, are those the details that, do we need to capture them? If the answer is yes, you might want to consider looking at an SPH method or smooth particle hydrodynamics. So when we have a multi-phase problem, and you can think of, for example, a washing machine, right? A seemingly simple device that we have in our kitchen, but in reality, there's a lot of physics on the fluid side happening, splashing and a wall film dripping. So we've got a lot of, say, F equal MA happening, and a tool like smooth particle hydrodynamics, which sort of analyzes the fluid as particles sort of combining together and then sort of separating, could be a more efficient tool. So certainly for multi-phase problems and for what we call volume of fluid or free surface type problems, an SPH method might help. Now, on the other side of things, we might have a mixture of liquid and solid. And an example there might be a packed bed, which is a common sort of design that we use in bioreacting and chemistry and processing industries, right? So for that, we've got quite a complex interaction between the liquid, perhaps there's gas bubbles penetrating, and we might also have, of course, some of the solid sort of particles in there. So we've got several different phases, and the overriding physics might be the collisions or contact between some of the solids inside the liquid. It acts like a liquid, but it is a solid. For that, we have a discrete element method, DEM or DPM, if you will, discrete phase. And that type of approach is a little bit better at capturing some of those sort of kinetics, if you will, between all of the small sort of particles bouncing off each other. So I think that of the three different methods, finite volume, smooth particle hydrodynamics, and discrete element, you can solve any problem, any phase, multiple phases. But I would certainly start with a finite volume, single phase, and then ask yourself, do we need to start to account for, say, liquid and gases or liquids and solids? And then you can go from there. But those tools, particularly the SPH and DEM tools, are really fast. And a lot of them, because they're newer, are actually built on GPU natively. So we're seeing some pretty amazing simulation speeds that we're not really used to in the finite volume world.
Absolutely. Question number 6. What is FSI and what is the criteria for using it over FEA/CFD?
Yeah, so FSI, fluid structure interaction, what what that method does is it solves the problem that that typical finite volume codes have, which is my walls are rigid, right? A lot of times we are trying to analyze something where the structure itself might be soft or flexible in some way. And so if we're just doing a traditional finite volume method, I'm pretty limited in my ability to capture moving walls. I can do it, but sometimes the underlying structure might be pretty flexible, right? Thinking like a composite, for example. Maybe some of the new aircraft that we have, that the wing is by design deflecting and has a different shape between being on the ground and being up at altitude. So for those types of models, we have to couple together our fluid analysis and our structural analysis, right? So a combination of, say, finite volume and finite element. Some CFD codes have the structures built in, which is great. You can do, say, a two-way coupling embedded in the software and get what you want. But a lot of times we're coupling, say, complex nonlinear FEA with CFD. That is a lot of fun. We've got a bit of experience in doing that, but you have to be kind of experts in both, right? You have to be competent in the level of CFD that you can understand how to troubleshoot that model. The FEA side may be a little bit more cleaner, but the reality is you're sending deformed meshes, you're sending deformed geometry back to the fluid solver. So you're really testing its ability to mesh.
Good one. And the last question, does an FSI model require a really large computer to solve?
Yeah, I mean, when we're doing fluid structure interaction, we're analyzing multiphysics. We've got a lot going on, right? We're trying to converge our fluid regime at the same time we're trying to converge our structural solid mechanics. So, does it require a large computer? Well, it all depends on the method. Sometimes we can put FEA on one computer and CFD on the other and have those two different pieces of hardware sort of talk back and forth. So by that definition, I suppose, because you need a second computer to do that. If you were to put the whole problem onto a single computer, of course, you're going to need to have a little bit more memory so that you can handle the entire problem depending on how the software works. Yeah, at the end of the day, if you've gotten to the point where you are conducting a multiphysics model, a structures fluid interaction model, you have to set the expectations that you're going to be solving a complex problem. It's going to take a little bit longer. You've got a heavy lift, so to speak. It's going to be relatively expensive from a compute standpoint. But at the end of the day, I think that saying that a computer is quote unquote really large doesn't mean a lot to a lot of people. Some people have quote unquote large computers at their disposal. Others have access to large computers per se, through the cloud or through a third party, service provider, infrastructure provider. So I think the concept of a quote unquote large computer is really being lost nowadays, right? Ask next time you talk to a young engineer, ask a young engineer if they even know how much RAM or computing power their computer has. They may not even know, and they may not even care. They just want to know that when they hit solve, the thing's going to converge and they can make a decision and move on to the next problem. So, I think the bottom line here is don't let the concept of a heavy computing lift or the need for a large computing power be a barrier to do multiphysics.
Sounds good. Thanks a lot, Jim. Appreciate it.
Awesome. Thanks, Yusuf.